So, welcome to lecture series on advanced linear algebra. We have seen the importance of invariant subspace to give a simplified structure of the linear operator defined over a finite dimensional space in terms of triangulability of the operators. This concept also can be utilized to a linear operator defined over a finite dimensional vector space, whether it is diagonalizable or not, that can be also proved by use of the concept of invariant subspace. So, what is that? It is like this. Let T be a linear operator on a finite dimensional vector space V over the field capital F. Then T is diagonalizable if and only if the minimal polynomial say P is product of linear factors of degree 1, that is P equal to x minus C1 into x minus C2 into x minus Ck, where C1, C2, Ck are distinct constant from the field capital F, or I can say distinct eigenvalues of the operator T. Already we have seen if T is diagonalizable, then minimal polynomial P is written in the form of x minus C1 into x minus C2 into x minus Ck. So, already we have seen if T is diagonalizable, then the minimal polynomial of T is of the form of star, that is P equal to x minus C1 into x minus C2 into x minus Ck, where C1, C2 and Ck are distinct eigenvalues of T. Now, we want to prove other way. Prove other way, that is if P equal to x minus C1 into x minus Ck then the operator T is diagonalizable. So, you want to prove this one please. So, I shall prove these results with the help of concept of our last lemma, last to last lemma, that is if T be linear operator defined over a finite dimensional vector space and the minimal polynomial is product of linear factors, that for any proper any subspace W which is invariant under T, if you consider any vector alpha belongs to V which is not belongs to W, the T conductor of alpha will be linear factors, linear polynomial please. I mean to say T minus Ci operating on alpha will be in W. So, I will use these results to prove this, the reverse one please. Let W1, W2 and Wk be the eigenspaces associated to eigenvalue C1, C2, Ck respectively. I mean to say Wi is the eigenspace associated to eigenvalue Ci, I equal to 1 to k. Let W is equal to sum of subspaces W1 plus W2 plus Wk. Let W is the proper subspace of V. Otherwise, the operator T will be diagonalizable please, because the space is spanned by the eigenvectors of the operator T. So, I have assumed that W, that sum of eigenspaces, is a proper subspace for V. I will say that it is not possible. Okay. So, let 0 not equal to alpha belongs to V such that alpha does not belongs to W. So, according to last lemma, what is that? If T be a linear operator defined over the finite vector space V, which minimal polynomial is product of linear factors, and if W is a proper subspace of V or any subspace of V, such that if alpha belongs to V, but alpha does not belong to W, then there exists an eigenvalue C such that T minus Ci operating on alpha will be in W please. So, I am not writing the statement of the lemma. So, I can simply say that according to last lemma, there exists an eigenvalue say Cj. So, certainly Cj will be from one of the C1, C2, Ck such that T minus Cj I operating on alpha will belongs to W. So, let beta equal to T minus Cj I operating on alpha, which belongs to W. So, this implies beta can be written as beta 1 plus beta 2 plus beta k, where beta I belongs to eigenspace Wi, and T beta will be T beta 1 plus T beta 2 plus T beta k, which is equal to C1 and beta 1 plus C2 beta 2 plus Ck beta k. In general, for any polynomial Hx over the field capital F, if you consider, then Ht operating on beta will be what? I can write down this will be equal to Hc1 beta 1 plus Hc2 beta 2 plus Hck beta k. Okay, so I will have Ht for any polynomial H over the F, Ht, this operator when operating on beta will be of this structure, please, and it will be in your W. For minimal polynomial P, we have P equal to, I can write down x minus Cj into something like some function, say Qx type. So, the minimal polynomial P can be written as x minus Cj into Qx. Based on our hypothesis, I will get a contradiction that x minus Cj divides Qx. I will prove that x minus Cj, this is a factor of the Qx, please. So, that our hypothesis that T is not diagonalizable will wrong. Okay. So, P equal to like this. So, this implies that if I consider Qx minus Qcj, so this is equal to, it will be polynomial such that x minus Cj will be factor, because put x equal to Cj, this is equal to 0. So, I can say this is equal to x minus Cj into some polynomial Hx, please. Since if I consider say Gx equal to Qx minus Qcj, then G at Cj equal to Qcj minus Qcj equal to 0. So, that is why I am saying that G have x minus Cj as a factor. So, I can write down Qx minus Qcj equal to x minus Cj into Hx form. So, this implies Qt minus Qcj I when it is operating on alpha will be equal to T minus Cj I Ht operating on alpha. So, Qt minus Qcj operating on alpha will be equal to this quantity, please. So, this is equal to, I can rewrite, because this is operator product, I can write these are commutative type. So, Ht into T minus Cj I into operating on alpha, please. But T minus Cj I operating on alpha equal to beta. So, this means that this is equal to Ht beta, since T minus Cj I operating on alpha equal to beta. So, Qt minus Qcj I operating on alpha is equal to Ht operating in beta. Beta belongs to W. So, HT beta will also belongs to W. So, this implies QT alpha minus QCJ alpha, which is equal to HT beta which belongs to W, please. My claim is that QT alpha is also belongs to W. How? We have 0 equal to PT alpha. If P is a minimal polynomial, so PT alpha will be equal to 0, which is equal to T minus Cj I into Qt alpha, please. This implies Qt alpha is an eigenvector provided Qt alpha not equal to 0. If Qt alpha equal to 0 implies what? Qt is the product of T minus C1i into T minus C2i, like that. So, this means that alpha will be annihilated by this, but I can say that then alpha will belongs to W. If Qt alpha equal to 0 imply alpha will belongs to W, because alpha will be eigenvector of the operator T, please, in that case, but alpha does not belongs to W. So, therefore, Qt alpha not equal to 0. So, Qt alpha not equal to 0 and the eigenvectors. So, Qt alpha will belongs to W, because it is an eigenvector and W is the eigenspace, sum of eigenspaces. So, this implies if I go to these expressions from I, we have what? We have QCj alpha, which is equal to Qt alpha minus HT beta. This belongs to, okay, in the right hand side each of them are belongs to W. This is also belongs to W, because Qt alpha belongs to W, HT beta also belongs to W. So, therefore, Qt alpha minus HT beta belongs to W. So, this implies QCj alpha belongs to W, but alpha does not belongs to W. So, this implies what? QCj must be equal to 0. So, this implies x minus Cj must divide Qx, which is not possible, because Q is there, Qx is basically the part of the minimal polynomial P excluding the factor x minus Cj, and the minimal polynomial P having only 1 degree factors, having on degree 1 only. So, T is diagonalizable. So, let us consider some problems. First problem or example type. Every matrix A, I mean square matrix of course, over the real line R, satisfying the relation A square equal to A is diagonalizable over R. How it is? If a square equal to a, this implies that the minimal polynomial of a is px equal to x square minus x, which is equal to x into x minus 1. So, P is product of linear factors of degree 1. So, according to last theorems, A is diagonalizable. Let me consider some more problems. Consider the indefinite integral operator T defined over the space of continuous function in the closed interval 0 1. Suppose it is given by T f of x equal to 0 to x f of t dt. So, this is my integral operator. I am taking this one place, which is indefinite integral operator T. Let W be the space of all polynomial functions over real line R. You will see that this W is a subset of space of all continuous functions. So, I can give its name as C01. So, W will be subset of C01. Not only subset, it will be also subspace of C01. Then what can we say about the T invariant of the subspace W? I mean, the space of polynomial function, when you integrate, will it remain again a polynomial functions? Certainly, because if I integrate a polynomial functions, I will get again a polynomial piece over the corresponding field. So, therefore, W will be invariant under T place. Certainly, W will be invariant under T. Since the integration of a polynomial function when the indefinite integral, of course, integral of a polynomial function gives again a polynomial function. So, that is why W will be invariant under T. Let me modify it. Let W1 be the space of all polynomial functions which are 0 at x equal to 1 by 2. I mean to say the x minus 1 by 2 is a factor of the each polynomial functions. Then do you think that W1 will be invariant under T? Then what can we say about T invariant of W1? Answer is no. Why? We have suppose if you take f equal to only x minus 1 by 2, then T f of x equal to 0 to x, if I consider simply t minus 1 by 2 into dt, then I will have what? This will give me t square by 2 minus t by 2, which is 0 to x, which is equal to 1 by 2 into t into t minus 1 and 0 to x is equal to x into x minus 1 by 2. This implies x minus 1 by 2 does not divide x into x minus 1 by 2. So, this implies that the x minus 1 by 2 factor which initially divide the given function f x is now it is not dividing to x into x minus 1 by 2. So, this implies that x into x minus 1 by 2 does not belongs to W1. So, you can solve many other problems which are given in the tutorial sheets and see the applications of concept of invariant subspace in diagonalization or triangulation of the operator, please.